But some people might also be absent in period 5. So going over logistics really fast before we go back into notes, section 9.5. I did just pass out your chapter 8 tests, so once again, those corrections are due Tuesday. That way, if you have any questions, you can ask me during lunch, preferably after school on Monday. You can maybe talk with some of your classmates Monday at the very beginning of class to see if they can help you out on a correction you got stuck on. But besides that, chapter 9, that's what we've been working on. Sorry, not Tuesday, Wednesday. And the reason why it's due Wednesday and not Tuesday is because as soon as we get back, if you guys have been looking at your homework sheet, there's section 9.1, section 9.2, section 9.3, section 9.5, and then there's a test review. Okay? Section 9.5, and then there's a test review. Remember I said at the very beginning, and maybe you don't, but I'm reminding you, at the very beginning of the chapter, this chapter is split into 2. There's a 75-point test and a 25-point quiz. Put them together, a 100-point chapter 9 assessment. Okay? 75 plus 25 is 100. So, the 75-point one is this one. That has to do with sequences and series. 9.1, 9.2, 9.3, and 9.5. 9.1 was introducing a lot of stuff, but really no formulas. It's more like recursive, how it looks and how we use it to jumpity jump jump. Nth term, what it is and how we use it to plug in n is 1 or 10 or 50. A sigma, summation notation, and how we plug in from the lower bound to the upper bound and solve. But then section 9.2, arithmetic sequences and series. Were there formulas? Yeah, there was an a sub n formula and an s sub n formula. I think that was it. Geometric, were there formulas? An a sub n, an s sub n, and an infinite idea / formula sometimes. Remember, the infinite only exists when it's approaching or stabilizing. What's that snazzy word for stabilizing? Converging. Good. And converging infinite sums will exist. Divergent infinite sums will not. But what makes the difference? Where it starts? Chris. Chris is saying, like, if the nth terms are going to 0. In a geometric, you could say that if we can make it go to 0. And what makes it go to 0? You guys were thinking this. The r's. If the common ratio is in between -1 to 1, then that part will go to 0, and I just steal the rest. So you could memorize, remember, for converging, a sub 1 over 1 minus r, but that's only for infinite and only when it works. So how many formulas? 5. In section 9.5, there will be 1 or 2 more. I guess it depends how you look at it. I guess 2. I guess we'll say 2. Why is it nice? Why is it nice? In some ways, that the test isn't next Tuesday, like this coming Tuesday, like we have spring break first. Why could that be nice? You have time to catch up. Yes, you have time to sleep and relax and kind of recuperate in your brain with everything that you guys have been facing this semester. But also, do you have a little bit of time? Could you make time, take time to memorize the formulas really, really well? Could you make time, take time to totally start the review early and come in this day with questions having fully attempted it? Yeah, because we're going to finish the very last section today. So the homework over the break is section 9.5, but what should I suggest, strongly suggest that you work on also? Yeah, work on the review, work on memorizing those formulas. There's no excuse for not having time at all to study. And even if you're traveling internationally, for instance, couldn't you take some pictures of the formulas or make a few cards and just put them in your pocket and be studying? Yep, you could. Believe it or not, I know exactly how long international trips take on plane rides and how much can get done if you choose to. But it is your choice. Okay, with that, aka my choir people, will you be taking a test on Tuesday? I think they might still be gone. You're taking it on Wednesday. Okay? Either Wednesday after school, so that you can ask me questions, or Thursday in class. Sound good? Either Wednesday after school, that way you have time to ask me questions. That way if you have any questions on the review, you can. Or Thursday in class. Cool? You get to choose. Are there any other choir people besides AJ and Jordan in this class? Oh, Joe. Okay. And the cool thing is there'll be a few of you guys, so you could always just like powwow on homework at some point. Now, I'm not saying necessarily you have to be like Dr. Clark. I can't sing right now. I can't minister because I have to do my pre-cal. Don't do that. That's a really bad idea. But just consider maybe before you leave, maybe taking like a picture of the review and just kind of playing with it a little bit on the plane ride. Like, just consider how you could kind of fit in a little bit of time. Okay. I do hear you and I do understand. I've required much more of calculus kids who have gone on mission trips with me, but not while they're supposed to be on the mission trip and serving, just as far as giving them a little extra time, but I can't just delay it forever. So please understand me. I hear you. It might be a little hard, but it's a really cool opportunity. I just can't give you forever. Kiddos, with that, we already saw the calendar. We saw what's coming. We saw what our responsibilities are and what would be a wise way of spending at least a little bit of time over break. Here we go. Section 9.5, binomial theorem. We got to go. Here we go. Pascal's triangle. I said it. You guys all groaned. Come on. It's not too bad. But let me explain to you why I'm not going to stop with Pascal's triangle. I'm not going to stop with Pascal's triangle. Pascal's triangle, you might want to write just a little snippet about it. What we call the binomial coefficients, the coefficients in front of the terms that occur once you expand a binomial. They do have a pattern, and it is called Pascal's triangle. You can write this basically just below what we did on the page before. If you guys did write down Pascal's triangle, let me just grab it real quick. Here we go. So there is a pattern. You see it right up above. You have my silly smiley face. Binomial coefficients do have a pattern, and this is what the pattern is. This is how it is displayed. This is how you can solve it. A lot of you guys caught on really quickly yesterday when I was talking about it. But just for the couple that might not have seen it before, what is the pattern and how did I get this triangle and how could I keep going? What's going to always be on the outside or coming first in every row? Ones are on the outside and ones are always where we end. What's going on in the second term? What's going to be the next second term? 1, 2, 3, 4, 5. What's going to happen when I get to this term though? Why is it going to be 10? You're adding the two values above that are, in a sense, on either side of the next term to come. So 1 and 4 makes 5, 4 and 6 makes 10, 6 and 4 makes 10, 4 and 1 makes, and I always end with a. Does that make sense? So I could keep on doing the pattern. If you guys notice this pattern, there are more patterns in the Pascal's triangle. There's 1, 2, 3, 4, 5. 1, 3, 6, 10. Let's do one more just to see it. That'd be 1, then 6, then 15, then 20, then 15, then 6, then 1, right? Do you guys see the pattern of this diagonal? Plus 2, plus 3, plus 4, plus 5. Ooh. Huh. How about this one? Plus 3, plus 6, plus 10. Is there any other way of thinking about it? Can't divide, can't multiply, can't do a squared. That doesn't work out so well. That's a nastier formula, to be honest. I can't actually remember what that one is. It's one of those nastier nth term ones. Can anybody see a formula for it? 1, 4. Anyway, within Pascal's triangle, there are tons of patterns and different ways of showing those patterns. Actually, Sierpinski's kind of comes out of Pascal's in some ways, and that was the fractal stuff we were talking about yesterday. But this is great. The pattern is great, and it's great if I'm doing any binomial to like the 3rd power, 4th power, 5th power, 6th power. But what if I was to ask you a question? Oh, sorry. Let me show you the pattern with all the variables in there. You don't have to write this down. Let me get rid of this page really quickly because we don't need it anymore. You don't need to write this whole thing out necessarily, but understand what's going on. the coefficients are talking about as long as you have a 1x plus 1y that's being raised to higher powers, the coefficients show what would be the coefficient for each respective term in the binomial, what we would call expansion, multiplying it all out. Not condensing into factored form, but expanding, multiplying it out. And as you guys notice, what's going on with the first term as you go, the first part of the binomial, as you're going term by term by term in the expansion, what's going on with his powers? They're always decreasing, going down by 1. Wait, what's his power here? No, what's x's power here?
Oh, 0.
0, until we finally get x to the 0 when he's gone. What's going on with y? He doesn't start at the highest, he starts at the, wait, he's not even there. Pause. What's his power? 0. And then 1, 2, 3, 4, 5. So the second term is increasing, starting at 0 and going up until it reaches the maximum capacity, which is the highest power. And the first term is starting at the highest and going down till its lowest capacity, which would be the 0 power. And the coefficients are in front. Now there are a few different things that'll make a binomial expansion look a lot different than this. But these coefficients from Pascal's triangle will always apply. The struggle is we can't stop with Pascal's triangle, because what if I was to ask you this? What if I was to ask you this? If I only taught you Pascal's triangle, this is 1a plus 1b, which is very similar to 1x plus 1y. So I can use the idea of what I just saw on the page before, but what's the problem in the example that could make it really tedious? 20th. 20th? So we have to go down to the 20th row? Now, could some of you guys go down to the 20th row? And the answer is, I believe, yes. However, do all of you guys want to go down to the 20th row? And I believe the answer is no. Now, if I was a really cool teacher like my high school math teacher, and we had tons of extra time, maybe I would get you starting to write a Pascal's triangle and give extra credit for whoever the next day would have the most rows expanded. It is. It was really nice and pretty until the numbers got really huge and then my symmetry got really off and then I got really disappointed and then I just stopped. But anyway, and we actually in honors checked it this year, I think for the first time. Checked it like at the very bottom row and my numbers got off. It was very sad. However, she still gave me the extra credit, so go team. That was good. But, hold on. 20th row, according to me, if I did it correctly so long ago, 1, 2, 3, 4, 5. I have the coefficient of the fifth term being 4,845. It's right here. The 20th row. I go down till I see the 20th, 1 and then 20. And I count 1, 2, 3, 4, 5. 485. Now, is that big of a Pascal's triangle? It's not that bad. But would it be tedious and kind of annoying? Yes. So what are we going to be really, really thankful for? This formula at the very beginning of the section that said, you know what, there is this thing called Pascal's triangle, there is this pattern, but there's a formula to let us jump ahead in Pascal's triangle to any term that we might want. There is a formula that lets us jump to whatever term that we might want. Now we're going to see if I'm right or not. 4,800 and, do you guys remember what I said? I have to go find it again. 4,845. We'll see if I'm right. And here's how we're going to see if I'm right. Whenever we're trying to find a certain term, jumping into Pascal's triangle, we have to ask ourselves 2 questions. Well, actually 4 questions total. We have to ask ourselves the following. What is the first term, which needs to go in this place right here? What is the second term, which will need to go in this place right here? Which you guys might think that's not a big deal, but here's the problem. Depending on what we have, we might need to actually plug in something a little bit nastier to the n minus r, something a little nastier than x, maybe like a 2x, maybe a 3a squared. We might need to plug in something a little bit more complicated than 1x or 1a. So we have to ask ourselves, who goes in this spot to the n minus r? Who goes in the second spot, which once again might be nastier than just a 1y? So we need to figure out who is the x, who is the y, and then who is the n and who is the r. There is a formula for how to do NCR. It's called a combination. It's actually in your calculator as well. There is a formula for NCR. P.S. Formulas you need to memorize for 9.5, and this is the other. I said there are two. I said two. Yeah, two. 1, 2. But we're going to have to ask ourselves those questions. But once we answer all those questions and put it in the form of a certain general term, we can find whatever we need specifically. So, coming over here, what do we know? Let me start off with what it looks like just straight out of our formula. Let's ask ourselves a few questions. I think it's easiest to figure out who is the x and who is the y first. So I'm going to write my c. I'm going to come back to that in a second. Who is the x? Who is the y? And we'll come back to everything else in a moment. Who's the x in this guy? A. So I'm just going to plug in, oh, all right. A to the, and who's my y? Easy. Now look at your formula. Who's your n? Good. Because it's a plus b to the, or x plus y to the, look at your formula, to the n. So this is equal to n. So I can put a 20 in that n spot, a 20 in that n spot. So what am I missing to finish this all off? Okay, so let's think about r. Sadly, it's not the common ratio because this isn't geometric. We're going to hear from Lainey and see what she thinks it is, but hold on, give me 1 second. Can I come back here for just a moment? Can I come back here for just a moment? I just said that this formula works for any term. I'm going to take this term and look at it just for a second. This is supposed to fit NCR, so 7CR with x to the 7 minus r and y to the r. This first term is supposed to fit this formula. My question is, what does r have to be for this term to make it possible? R has to be 0. Because who's not there? The y. So r in this one must be 0. This would be 7c0, x to the 7 minus 0, y to the 0. Does that make sense? X to the 7 minus 0 is x to the 7, y to the 0 is going to be gone, so just x to the 7, and then we have some coefficient. We could plug into the formula and make sure that it makes sense. What's the formula that you guys have written down for how to solve NCR? Oh, r factorial. Let's see if it makes sense and if it's really the one. Okay? If I was to simplify, I'd have 7 factorial all over 7 factorial. Wait, what's 0 factorial defined to be? Oh, what's 7 factorial over 7 factorial? And what is 1? My coefficient. You might be like, okay, that was lucky. All right, fine, hold on. If r is 0 here, and if r has to do with the power of y, question, what would r be at this term? So this term would be 7c4, x to the 7 minus 4, x cubed, y to the 4. To check 7c4, tell me your formula again. NCR is equal to, good, n factorial, 7 factorial, all over, n minus r factorial times, which would equal, hold on, 7 factorial all over 3 factorial, 4 factorial. Hey, let's practice. Can't I cancel out the 4 factorial with everybody up till 5 and 6 and 7? All over 3 and 2 and 1. Remember how we practiced this? Isn't 3 and 2? What's 7 and 5? With this little NCR, we can jump anywhere in Pascal's. Wait, let's use that for what I was saying I think my Pascal's triangle tells me for the example. But first, Chris.
When you went from 7 factorial over 7 minus 4 to 7, yeah, right there. Wouldn't that be, oh, wait, never mind, yep.
You got it?
Yep.
Yeah. You might have been thinking of don't distribute. Okay, so let's come back and figure, wait. Which term was this in the expansion? This guy. First term. What was R? What term is this guy? First, second, third, fourth, fifth term. What was R? R is always going to be 1 less than the term where you are. Hey, how does that help with our example? You guys looking at it? What term do they want? The fifth degree of A. Oh, wait, they didn't say the fifth term. They said the fifth degree of A? What does that mean? They want A to be raised to what power? Oh. So it's not the fifth term. Okay, hold on. So I can't just set R equal to 4, which is the number I was looking at over here. I thought it said the fifth term, so I said the binomial for the fifth term. They want when A has counted down from 20th all the way down to 5. Oh, stink. What term is that going to be? Would that be kind of hard to count? A to the 20th, A to the 19th, 18th, 17th, 16th. Wait. Can't we just say that we need A's power to be 5? Oh, nice. I know, you were all saying it. I just need to make sure that people understood how you got it. So now we can go ahead and plug and chug. And as you guys plug and chug, now that we know what R is supposed to be, use your formula for NCR. 20C15 times A to the 20 minus 15 will be 5. Booyah! Fifth degree of A. B is going to be to the 15th. P.S. If you guys notice, the powers of the two terms will always add to Bn if you did it correctly. The powers always add to Bn. And why don't I look at my little Pascal's triangle? Uh-oh, I have to go backwards 5 terms and see if I agree. The 20th row. Backwards, 1, 2, 3, 4, 5. Hey, it's the same term. How come? Because Pascal's triangle has symmetry. It goes up and then it counts back. So let's see if we got it. You guys are trying to find 20 factorial all over. 20 minus 15 factorial, 15 factorial. Ooh, I see this 15 factorial canceling with everything but 16, 17, 18, 19, 20. All over 5, 4, I guess I should have counted up, sorry. 5 and 4 is 20. Go team. 3 and 2 is 6. 6 and 18 is 1 and 3. 3 and 16 is 48. Anybody throw that in? What do we get? Uh-oh. My mental math skills are going to be a little too tired for that today. If I had pencil and paper, I'd get it pretty quick. 16 times 17 times 19 times 3. Ooh. My Pascal's got off early. 15,504. Well, it makes sense why my end one was wrong. That's very sad. Oh, no, it is right. I just can't count. Huh, go team. 15,504. Oh, well. 15,504. Good job. Because I counted wrong. 5th, 4th, 3rd, 2nd, 1st. It'd be 6 terms from the end, not 5 terms from the end. Okay, let's play some more. Ooh, okay, this page just says play with the whole NCR formula. Play with the whole NCR formula. So you guys, go ahead and play. I'm going to go ahead and freeze the screen, and I'm going to do it too. I'm going to hide the screen over here so you guys can't tell what I'm doing. And then we'll check the answers in just a second. So play with NCR. if you finish earlier, go see if you can find where the NCR formula is in your calculator. Because if you're allowed to use your calculator on an NCR problem, there's a function for that. I'll give you a hint. It's very mathy. It's very mathy. All calculators have it, old and new. All graphic calculators have it, old and new. You ready? Oh, getting there. Oh, but the 15 makes sense. The 15 gets plugged in the R spot and in the R spot, and then 20 means 15. How about now? You guys agree?
Oh, heck yeah.
Took me a little bit. The 6 canceled, the 7, 8 were left. The 7 factorial canceled, 10, 9, 8 were left, all over 3 and 2. The 2 and 8 became 1 and 4, the 3 and 9 became 1 and 3, 12 and 10 is 120. And then these were nice because 0 factorial just became 1. 0 factorial just became 1. So then those reduced. Those reduced. Dun, 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 dun. Okay, where is it in the calculator? Math? Probability. It's going to come back in our quiz after spring break 9697 probability section. It'll come back and be used some more for some probability stuff, but for right now, there we go. Okay, question. How do we do the expansion of the expression? What are they asking us to do? Find one term or find all the terms? Find the expansion, all the terms. Could we multiply x plus 1 times x plus 1 times x plus 1? Yes. Could we also say, hold on, there's a pattern. Pause. Is it really hard to get to the third power row in Pascal's? So if that's faster for you, do it that way. But if you wanted to do it the other way, you could do this as well. 3c0, x to the 3, 1 to the 0, plus 3c1, x to the 2, 1 to the 1, plus 3c2, x to the 1, 1 squared, plus 3c3, x to the 0, 1 cubed. Now, I'm showing it to you this way just so you understand the pattern. It's a pretty easy example. Do you see how my first term started at the highest and counted down? Do you see how my second term started at the lowest and counted up? And do you see how my NCRs, my N's always stayed the same. My R's moved based on the power of my second term? But what's that going to end up being? Well, what are these C's going to become? Nice. So it's going to be 1x cubed, well, that's just going to be times 1, plus 3x squared times 1, plus 3x times 1, plus 1 times 1 times 1. So I get x cubed plus 3x squared plus 3x plus 1. I did the C's using Pascal's because it was an easy row to get to. But I would have plugged into my formula or my button in my calculator if it had been something like the 19th power or the 15th power, because that would have taken way too long. Does that make sense? So we can do that for any expansion, but this one was still kind of easy because I had a 1x and I had a 1 and it was a plus. I wonder if the next one will be a little bit harder. I wonder if the next one will be a little harder. Woo! I think we need to identify some stuff. Now here's the struggle. Are they looking for one term or all the terms? Yeah? But we can tell this is more complicated, right? All right. So let's just think in general about the term. In general. NCR, x to the n minus r, y to the r. Okay, r is always changing, so let's just leave him to be an r. But what can I make the n's, first of all? Good. Because I'm raising to the 5th power, so I can make my n's 5. My r's, remember, they change. If they start at 1, then they go to 2. Oh, nope, they start at 0. Go to 1, then 2, then 3, then 4, then 5. So forget the r's. What's going to go in this spot? 3a. Nicely done. What's going to go in this spot? Nice. Negative 4b. Because, look at your formula. Isn't it a plus b or x plus y? So if I was to rewrite this, I would need to rewrite it as 3a plus a negative 4b. Now, I can't say it's equal to one term, but I can say that's the general formula I'm going to use. So check it. Is anybody getting kind of annoyed with the NCR notation? Okay. Did you pick up on how there's another way of writing it? Yeah. Careful, not r over n. You could also do it this way. It's not a fraction. It's just notation for 5c0. It's just notation for 5c0. So we could write it this way if it's a little bit easier for you. Then we could do, wait a minute, 3a is going to start off for what power? Or to what power? Careful. He starts off to the highest. R starts off at 0, so 5 minus 0 would be 5. What does negative 4b start off with? So can I just not write them? Is that okay? Who's going to show up now? Yeah, well, careful. The negative 4b, right, is now raised to the 1st power. Plus 5c2. What power is 3a going to be raised to now? What power is negative 4b going to be raised to now? Good. 3a is going to be raised to the negative 4b is going to be raised to the... Oh, it's okay. I have a smart board. You guys hopefully have more paper. I know it's going to be a little bit thicker. Don't judge. 3a to the 1, negative 4b to the 4. 3a is now gone because it's now to the 0. And negative 4b is going to be raised to the 5th. Does that make sense? Now question. If it's not too hard to get to the 5th row, if it's not too hard to get there, why isn't the expansion going to literally look like 1, 5, 10, 10, 5, 1? When we finish this, why isn't it going to look like that row? There will be maybe some minuses, right? There might be some subtractions, not additions, but besides the signs, why else will those numbers not literally be what's showing in the answer? What do you notice? We have other numbers that have come in from the terms. So when we go to solve this one, yes, from Pascal's, or using the NCR formula, I could change this to be 1, I could change this to be 5, I could change this to be 10, I could change this to be 10, this to be 5, and this to be 1. But do I have more numbers in every single term that are going to have to be a part? Yes. So what would my first term actually be? 3 to the 5th times a to the 5th, right? And so plugging in 3 to the 5th, we end up with 3 to the 5th, choop, choop. 243 times 1 is 243 a to the 5th. Does that mean the formula doesn't work? No! It just means the 1 got multiplied by somebody else. right? Why is the next term not going to be a plus, but instead it's going to be a minus? I have a negative to the first power. And my coefficient is going to be 5 times 3 to the 4th times 4. Well, technically, negative 4. We end up with 1620. A to the 4th. B. Was the 5 not important? No, it was crucial. But I also had 5 times 3 to the 4th times 4. Negative 4, hence the negative. Do you guys get the same thing as I did? Who's getting the next term to double check me? I just put my times 16 in an exponent. That's really sad. Times 3 cubed times... Yep, I got it too. Thanks, Lainey. Plus 4,320. A is now cubed. B is now squared. Who is the next term? Yeah. Why is it negative? That one was positive. Yeah, when the negative is raised to an even power, they pair up. A negative times a negative is a positive, but odd powers, going to be negative. So this next one, another even power, is going to be positive. Who has it? A times B to the 4th, right? No. I wrote something wrong.
Yeah, 3.
B cubed, thank you. There we go. So now AB to the 4th. And then the last term? But it's a negative, right?
Negative.
Good. Do you guys also notice that even though this has symmetry, once you have different numbers being raised to different powers, you don't still see symmetry in the numeric answers? You see the alternating signs, positive, negative, positive, negative. You still see the A's counting down and the B's counting up, but the numbers get a little messier. Does that make sense how the pattern works, though? Kind of. Ooh. Wait. But we don't have to do the entire expansion. Now, could we? Yes. We could do the whole thing and then count over 1, 2, 3, 4, 5, 6, 7, 8. This guy. Done. Or we could try to jump. Let's make sure that we're focused. We could try to do the entire thing, or we could try to jump. Joshua, hood off. Thank you. So if you guys want to do the entire thing, go. Have fun. The rest of us will try to jump. And we're going to jump to, does it make sense? I'm doing 9CR, 4x to the 9 minus r, 3y to the r. Does that make sense? I got my first, zoop, my second, zoop. It's a positive, so no negative. And n was 9. Now, you see this n, but really that's just saying, hey, it's this term. I'm sorry. N gets used for a few things this chapter. But the power still goes where the power needs to go. This is just saying, look for the 8th term. Wait, we talked about this. We need r, and we know we're going to the 8th term. What's going to happen to r's value if it's at the 8th term? Careful, r starts at not 1. R starts at 0. So starting at 0, I mean, if worst comes to worst, 0 is the first term. 1 is the second term. 2, 3, 4, 5, 6, 7. R equals 7. Remember how I said r is always 1 less than the nth term? Or the th term if you don't like using n? Because r starts at 0. If r started at 1, this would be 8. But since r starts at 0, 0 counts as the first. So we're saying, oh, the 8th term just means r equals 7. Easy. So we can just go ahead and do 9c7. 4x to the 9 minus 7 is 2. 3y to the 7 is, well, 3y to the 7. Okay. So you guys can go find that NCR button, or we could just go ahead and have some fun with factorials. That'll end up being 16x squared. This will end up being, I don't know, 3 to the 7th, y to the 7th. That's going to be 9 times 8 all over 2 times 1, which will end up being 36 times 16x squared times, I don't know, 3 to the 7th, y to the 7th. Someone get me a nice little number for this guy with x squared, y to the 7th. 36 times 16 times 3 to the 7th. Just kidding, I got way too in front of you. Here, Ryan, you and me. Let's see if we get it. What'd you get? Oh, no, you're okay. Look at all those numbers at the bottom. We're just multiplying them all. Okay, what'd you get? Me too. So 1,259,712. Dun, 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 dun. Oh, we could have done the whole expansion and counted and found him. Ugh, that would have been gross. Binomial theorem. Does it let us expand whole binomials raised to powers? Yes. Does it let us jump places? Also yes. Ooh. Maybe a homework help we won't get to. Maybe we will. You can just look at it. You can just look at it. But shush. Who's R? Why am I circling the y squared? Oh. Plug it in, done. All right, cool kids. Homework due the day we get back. Happy Thursday, almost. It is basically Friday. Brace fail, I think. See you guys later. Work on your test corrections and homework.